In this video, I want to introduce the central concepts around which this course is built. And I want to begin this by talking about something called threshold concepts. So threshold concepts are something that come from the research and theory of higher education. They are an idea that was introduced, I think, about 15 years ago by Jan Meyer and Ray Land. I remember buying the book that they published back then that introduced those ideas, and everyone was very excited about it at the time. These days, I'm slightly skeptical about the detail of this concept and how it's developed, but I think it's a useful way of understanding something about the process of learning. So the key idea is that there are some types of generally quite complex skills and concepts that are very difficult for most people to initially grasp or obtain. But once you've got them, they kind of open a door so that you can see new things and you can see things in a new way. And many disciplines have concepts that are like this. Now, what I want to do in this course is help you or guide you to obtain what I think are 6 concepts or mixtures of concepts and skills that fall into this category. And I won't go into a lot of detail about them here, but I'll just describe them briefly. By their very nature, we need to spend quite a lot of time on them before you really got the hang of what they meant. So the first one is a geometric understanding of data in terms of shapes and distances. So people who are data analysts, who are statisticians, who work all the time with data, they develop this way of seeing and thinking about data. It's kind of in spatial terms. It's the way they relate to it. And once you get this, then a lot of other things become easier to understand. And it becomes easier to work with data and think about whether it's good or bad and how 2 different pieces of data relate to each other and so on. So we get this by practice and by learning some simple techniques that will help us. The second one is the Bayesian model of updating belief on the basis of evidence. This is a core part of the sort of central logic of science, of how we take new evidence about things and we use it to test and change and update our belief. There is a strong mathematical basis to this. We don't go into that in any detail. I will show you how to do a simple calculation with it, but the most important thing is actually learning to think this way, learning to weigh up evidence and learning to see how evidence might be misleading. The third thing is statistical inference. Now, statistical inference is something that we hope that anyone who does an introductory course in statistics will come away understanding. But it's surprising a lot of students don't. They'll spend a whole semester studying an introductory statistics course, and they spend so much time on calculations and memorizing things and so on that they kind of miss the big picture. So I want to kind of tip this on its head and focus on the big picture. And I've spent a lot of time trying to identify techniques that I can use for doing that. And I've been successful, I think, in some other courses I've taught. And it went, I think, pretty well in this course last year. So I'm going to do it again this year. An example of what we mean by statistical inference is there was a recent poll by a big polling company called Ipsos. They did a whole lot of surveys around the world of people's attitudes to the current Tokyo Olympics. And in Australia, they took a sample of 1,000 people, I presume adults. So Australia has a population of around 25 million. So this is a tiny, tiny, tiny sample of Australia's population. But it was a sample that was carefully selected to be representative of the population as a whole. Now, when you take a small sample from a large population, you can get evidence which you believe is representative of the population, but it's not going to be exactly representative. There's going to be some error because you're only working with a sample. And we call that, that error has a technical name, which is standard error. And in this case, what they found with one of their questions was that 45% of the population were not interested or not very interested in the Olympics. And the standard error for that, the error that came from the fact that it was just a sample of 1,000 rather than the masking the whole population, was about 1.75%. And once we know that, once we've calculated that standard error, we can do another calculation and we can come up with something where we can say that we're 95% confident that the proportion of the population that's not interested in the Olympics or not very interested is 45% plus or minus 3.5%. That's the basic mechanics of statistical inference. But we will learn a couple of techniques that are very useful with the kinds of data that you come across regularly that you can use, and they don't involve terribly complicated calculations or computer software. And I think they'll be useful. But the main thing is I actually want you to get this intuitive understanding that, you know, samples have to be representative, and even if they are representative, because they're samples, there's going to be a degree of error or imprecision, and that you need to know what that is. The next one is about measurement levels. I'm not really even going to try and explain what that's about at the moment. I'll just point out that it's not as obvious as most people think. It's usually dealt with in a pretty cursory way in introductory research methods and statistical courses, but it's a cause of a lot of bad data and bad evidence in the business world. And so I think it's important to have a somewhat more sophisticated understanding of it. So we'll spend some time on that as well. The next one is a big one. This is about understanding the interrelationship between the ideas of causation, one thing causing another, correlation, information, and prediction. These are very important topics. I don't think they're terribly well explained very often. People, you know, lecturers will say to you, oh, you know, correlation is not causation, but that's actually quite an oversimplification of the real situation. And I think, again, a bit like measurement levels, it's important to have a more sophisticated understanding. So we're going to work on that. The final one is quite different. This is a much more narrow threshold concept, but I think it's a really useful one to know. And I've found from the teaching that I've done of MBA students in Australia and also in China, where I've been running an MBA program for the last 18 years or so, with people who have run actual businesses and are senior leaders and so on in organizations. They find this really useful. Just a practical thing, if you understand how it works. I've found a way of a tool that you can use that doesn't involve complicated calculations, but it's very versatile. And so we'll get to that one towards the end of the course, because it just builds on the earlier ones. Once you've got the hang of these earlier concepts, statistical process control is not terribly difficult to grasp. So in terms of the motivation for these, really important thing is that when we make decisions, the decisions are kind of inseparable from an understanding that what we decide to do is going to have some kind of causal effect. We decide to do something because we think it will cause something desirable to happen or prevent something undesirable from happening. That's what decisions are about. And so we have, with any decision, we have a belief about causal relationships. And beliefs about causal relationships have to be based on evidence. And much of the evidence that we use, not all of it, but much of the evidence takes the form of data. And so that's why we have the emphasis in this course on those things. Now, in terms of teaching all of this, one problem that we have is that, you know, these 6 central threshold concepts, to some extent, they are interrelated, and understanding one helps you understand others better. So there's a question about what order do you teach them in. And I've tried to pick what I think is the best order, but what it will mean is that in the early stages of the course, some things might seem rather difficult or perhaps a bit vague, but they will become clearer as we work our way through these concepts. So I'm just giving you a little heads up about that. The other big thing we're going to do in this course is learning to appraise the quality of scientific literature. Now, this is important because it's useful, and it's important because it's an expectation, or will be an expectation of you as students and graduates of a leading research university of international standing. It's expected that you can make some kind of sense of academic research literature. Now, in the management area, most of the really important academic research is published in academic journals. And the nature of the way it's published makes it very inaccessible. It's hard to read, it's hard to understand. The authors are not writing for students, they're not writing for people who work as managers in business. They're not even writing for a broad academic audience. They're writing typically for a very narrow, specialized type of academic who is doing the same sorts of things that they are, okay, that shares the same sub-discipline. They use terminology that's very specific. A lot of academics, not all of them, but a lot of them are just not very good at writing clearly. Even if you take away all the jargon and so on, their writing skills are actually not that great. And there's a few other problems. There are some disciplines where the theory is pretty fragmented. If you look at many of the sciences, particularly say the physical sciences, there's very clear theories about a lot of things. So in physics, for example, there are many areas where the theory is very well established, it's very clear, it's set out as equations. And if you're doing research in physics, you've got a really solid foundation of theory on which you can build. In management, that's just not always the case. There are many interesting areas where there are competing theories, and a lot of the theories are not complete. And some of them are not on very solid ground, and academics argue about them. And the nature of academic publishing is that the top journals, the most highly respected journals, their main interest is in getting things published that are interesting to their readers. And that creates a premium for research that is novel and really interesting, but it doesn't actually encourage people to work together to sort of fill in all the perhaps sometimes boring gaps in the theoretical picture. And that's why you get this fragmentation. The final thing is that in management, a lot of the research is quantitative, and it often uses really complex and sometimes obscure statistical methods, sometimes for good reasons, but I think sometimes not necessarily for good reasons, more to make the study look more sophisticated than it really is, or to try to extract the best possible result out of some data that is maybe not of the highest quality. So you have to, you have to sort of get a bit of a second sense about what's going on when you read a paper about these sorts of things. Now, I can't teach you all of this, but we will look at examples. What I want to try and do is start you on what'll probably be a sort of career-long journey, I hope, of getting better at this and learning your way around these things. But I think we can do enough in one course to actually give you a pretty good head start, and I think perhaps give you some advantages over students who don't get this kind of training. Okay, that's it for this video. In the next one, I'll talk about the assessment for the course.